Hello everyone, welcome back to CS 11747, Neural Networks for NLP. This time I'm going to be talking about generating trees or graphs with neural networks. So why would we want to model trees and graphs in NLP in the first place? So there's many reasons. These are very general data structures that can be used to represent a lot of different phenomena. But here I'll introduce two of the most commonly used and broadly applicable ones. The first one is syntactic structure, and syntactic structure explains kind of how sentences are built up. There's a number of different ways to represent these, including dependency trees, which represent the relationships between the words in a sentence. So for example, here we have saw is the main verb of the sentence, and it has a subject, I, an object, man, and a prepositional phrase starting with. So this would be one example of a syntactic structure. Another example of a syntactic structure would be a phrase structure tree, which specifies the different phrases in the sentence. So for example, this is specifying that with a telescope is a prepositional phrase. Another thing that we can model is the underlying semantics of utterances, and there's many different ways of doing this. And I'll talk about this a little bit in a bit, but for example, if we have a natural language command, we could parse it into a tree structure corresponding to a program that executes the intent of that command. So this is the underlying semantics. It's the thing that you wanted the computer to do based on what you told it to do in natural language. Okay, so why would we want to model syntactic structure? So what we've seen in previous classes is that regular models over word sequences do quite well, but they may not capture phenomena that inherently require structure, such as long-distance agreement. So in English, plural nouns and singular nouns have different verb conjugations. So in order to manage this, we need to see that parts of the river valley basically corresponds to parts and corresponds to this verb. So we would need to have a plural conjugation here. But regular sequence-based models might have a problem with this because there's a couple singular nouns that intervene. And you can see that indeed this is the case. If you have an appropriately structured syntactic model, you're able to handle this. This is important for robustness and generalization of models. And you can see that this model, essentially functions better in the situation where we have kind of long sentences or difficult phenomena. Another reason why we might want to use syntactic structure is, for example, if we have a human in the loop of the system, and the human would like to say, well, if a particular noun is the subject of a particular verb, then I would like to have a rule that does a particular thing. And this is a lot easier to write if you have a concept of syntax than it is to write just based on the words that exist in the sentence, for example. For semantic structure, there's a number of different types of semantic structures, so it's a little bit harder to say, this is the use case for it. But to give an example, like I did before, we have a natural language sentence and a source code utterance here. And we have a structured meaning representation in tree format corresponding to the source code. And if you were able to model this semantic structure, you could essentially write programs or do database queries or something like this with a computer. And this is actually very widely used in question answering systems, for example, that are making queries against databases or controlling robots or something like this. Another reason why you might want to use it is the reason that I talked about before, which is if we want a human in the loop to basically be able to write rules over particular structures, knowing that who did what to whom, for example. You could extract all examples where, for example, a person did a particular action to an object, like a person sold stock of a company or something like this. And these would all have, sentences describing this would all have different surface forms, but if you were able to model the underlying semantics, you would be able to handle this. So parsing is basically predicting some sort of structured output from an input sentence. And there's a number of different models for parsing. These can include things like transition-based or incremental models that step through actions one by one until we have an output. And this could be a little bit like a history-based model for part-of-speech tagging or an encoder-decoder model that makes predictions of the next word one at a time. And you can also have graph-based or dynamic programming-based models. And these calculate the probability of each edge or constituent or something else and perform some sort of dynamic programming. And these can be like the CRF-based model that we talked about for part-of-speech tagging. So I'm going to go through a couple of these models, but please, think back to what you already know about sequence labeling or sequence tagging models, and you should be able to make the connections there. So first I'm going to talk about shift-reduce dependency parsing, and this is a transition-based model or incremental model for parsing syntactic structure. And so one question might be, why would we want to handle this structure in the first place? And I briefly alluded to this, but dependencies can be good for semantic tasks where words are close in the tree. So you could, write rules over a dependency structure that allow you to extract, subjects and objects of verbs or something like this. And you can create labeled dependencies like this that explicitly tell you that I is the subject of saw, or girl is the object of saw, and this prepositional phrase connects to saw, for example. So to give one example of how we could do this with a probabilistic model, there's something called shift-reduce parsing. And shift-reduce parsing basically processes words one by one left to right and distinguishes the dependencies that correspond to each word. And the way it works is we have two data structures. One is a queue of unprocessed words. Another is a stack of partially processed words. And at each point in the decoding process, we choose one of several actions. The first action is shift, which moves one word from the queue to the stack. The second is reduce left, where the top word on the stack is designated as the head of the second word. And reduce right, where the second word on the stack is designated as the head of the top word. And we learn how to choose each action with a classifier. Okay, now I'd like to go into an example of this to make it more concrete. So let's say we have on the buffer here, which can also be used interchangeably with the queue, we have all of the words in the sentence. And on the stack, we have the root, special root token corresponding to the head of the actual head of the sentence. So the first thing we do is shift, move the word I onto the stack. We shift again, moving the word saw onto the stack. And then we do the left action, which makes a left pointing arrow from the two top stack elements. We shift again to get another word on the stack, shift again, and then we do left to make a left pointing arrow between the top two stack elements. We do right to do a right pointing arrow between the top two stack elements, and then we do right. And now we have a single item on the stack, no items in the buffer, which indicates that we're done parsing. So you can see if you choose the right actions, then we will get the right sentence. And so in order to choose these actions, we basically want to train a classifier that will get the actions correct. So given a configuration, which is essentially the stack and the buffer items, we want to choose which action. So we can shift, do a left or a right pointing arrow. And as I said, we want to pick the right actions and then we'll get the right tree, but this is, of course, a highly non-trivial task. So the way we make classification decisions is we extract features from the configuration, such as what words are on the stack or buffer. We could also do things like what are their part-of-speech tags or children. And it's also important to know feature combinations, as it is in many of the other NLP tasks that we've thought about so far. So for example, if the second word on the stack is a verb and the first is a noun, then the right action is likely because it's very common to have nouns be the children of verbs. So combination features used to be created manually, and you can see this Zhang and Nivra paper to see the types of combination features that people created. But now we can just use neural nets. So an early attempt to do this essentially used a feed-forward neural network to feed in all of the features that were used in previous systems, like the words on the stack or the buffer, the parts of speech, and also arc labels. And then they let the neural network do the feature combination. But one issue with this is you still need to know what underlying features you want to be using, like words or part of speech tags, when in fact we would kind of like to let the whole feature extraction process be left to neural networks. So before I get into exactly how we do this, I'd like to make a brief aside about how we could use tree structures or graph structures in neural networks. And one example of this is syntax-driven composition, or syntax-driven extraction of combination features. So why would we want to use a tree structure? One example of this is in this example here, and this is from the Stanford Sentiment Tree Bank, where basically we have a sentence with words, and then we have the individual sentiment for each of the underlying phrases in the parse tree. And what you can see is we have something like lacks in depth, which is a very negative sentiment. Empire lacks in depth is still a negative sentiment. But then over here we have its heart, or it makes up for it with its heart. So basically this is a very positive sentiment. So you can see that essentially we could almost even come up with rules, which is that if we have what blank, it makes up for in blank. So we have kind of a generalizable pattern of how you say something negative first, but then follow up with something positive. Or say something positive first, but then make up for something negative. And if you just looked at the words in the sentence, you might be thrown off by kind of having a negative word somewhere in the sentence, despite the fact that the whole structure tells you it's positive. So this is just one example. There are many, many other examples of this in natural language. So one way to use this tree structure in neural networks is using something called recursive neural networks. And what these do basically is they take the syntactic structure of the sentence, and instead of doing, for example, a recurrent neural network from left to right, one word at a time, they follow this structure. So the smallest phrase in this sentence is "this movie." And so what you do is you take the two words in this phrase, combine them into a single representation for the entire phrase. You could then gradually step up the tree and combine together the subphrases in the tree. And specifically, you could run this by concatenating the two kind of underlying representations here and running them through something that looks like an NLP with a nonlinear function. You could also do a bunch of other things. So like if you knew the types of the phrases, so if you knew it was a noun phrase or verb phrase, you could also parameterize the neural network differently by each of these phrases. This was expanded to long short-term memory networks to help prevent gradient propagation issues. So basically, there's the child sum tree Lstm, where parameters are shared between all of the children, possibly based on grammatical label, etc. And basically what this does is this runs in Lstm, but instead of having a single input like the traditional Lstm, it has all of the individual children. Notably, the forget gate is different. Forget gate value is different for each child, so the network can learn to ignore children and give less weight to particular nodes in the tree. There's also n-ary tree LSTMs that have different parameters for each child up to n, which is a little bit like the tree RNN. So another way you can do composition is, like, let's say you have several different children. You can just run each of the children through a bidirectional LSTM and use the outputs of the bidirectional LSTM to generate the representations for each phrase. And there's also methods that use attention in follow-up papers as well. So basically, the idea here is that the tree structured LSTM, it has a bunch of children that correspond, a bunch or two or more children that correspond to a particular head node. And then you just compose them together using some sort of sequence to vector function, be it by LSTM, attention, or something else, and do this gradually up the tree in a recursive manner. And we have an example of this implementation in treelstm.py if you want to take a look at it. So now that we know how to do this, and these sort of tree-structured composition functions can be used for all kinds of different things. They can be used for like text classification or other applications. But if we wanted to use them for parsing, we can do so as well. And as I mentioned, we don't want to be doing feature engineering. Why do we want to, look at only particular parts of the tree when we're doing our parsing? So we could, theoretically encode all the information we need to do parsing with a recurrent neural network or recursive neural network. And as I mentioned before, if we're doing shift-reduce parsing for dependency parsing, for example, we'll have the stack in the buffer and all of the actions we did before. So one example of this is something called the stack LSTM or stack RNN, where essentially we encode the stack with and the buffer and all of the previous actions. So the buffer is relatively simple. It's just all of the words that we have seen so far, and we can run a backwards LSTM here to get the encoding. We can also have the previous actions. So this is just all the actions we've done before. We could use a simple LSTM or recurrent neural network to encode this. And the stack is a little bit more complicated. So the stack here, we're not only encoding words, but we're also encoding subtrees of the tree. As you remember before, at any particular point in the parsing, we might have these kind of subtrees on the stack. So the way we can do this is actually relatively simple conceptually, maybe a little bit more difficult computationally, but what we do is we essentially run any tree-structured composition function that we would like to encode this subtree, which can then just be fed into an LSTM or any sort of sequential network. So I realize this is, somewhat complex, but hopefully this gives you the high-level idea, and you can go back and read the papers if you'd like for more details, if this sounds interesting to you. Okay, so now I'd like to shift gears a little bit to dynamic programming-based models for phrase structure parsing. And so one thing I should point out is there are shift-reduce models for phrase structure parsing, dynamic programming models for dependency parsing. But just because of the evolution of the field and also maybe some computational concerns, it tends to be the case that shift-reduce methods are used relatively widely for dependency parsing, and dynamic programming-based methods are used relatively widely for phrase structure parsing. So I'm going to introduce the dynamic programming methods from the context of phrase structure parsing. So phrase structure parsing in the first place are models to calculate phrase structure, as I mentioned before. And basically what we do is we start with kind of part of speech tagged individual words, and then we compose them into longer phrases. So like the determiner and the noun telescope become a noun phrase, a telescope. We add with, and this becomes the prepositional phrase with a telescope. And then we can combine a verb, a noun phrase, and a prepositional phrase into a verb phrase, for example. So an important insight here is that parsing to these trees is similar to the CRF based search algorithms that we used in a couple lectures ago. So tagging, as formulated in the CRF-based dynamic programs, was tagging is search in a graph for the best path. So you'll remember we used the Viterbi algorithm to search for the best path through a graph. But here, parsing is search in something we call a hypergraph for the best tree. And I mentioned this briefly in the CRF lecture, but let me go into more detail here. So what is a hypergraph? A hypergraph is basically a generalization of a graph structure. And the degree of an edge in a graph is essentially its number of children. So for example, we might have a degree 1 where we have a preposition. Sorry, my slide is broken. This should be like with or something like that, or I, sorry. And here, this would be saw. And then degree 2, we would have an edge, but it has 2 children. So we would have a verb phrase, but we would have a verb and a noun is its child. And then degree 3 would basically have a verb, a noun phrase, and a prepositional phrase. So the degree of a hypergraph is the maximum degree of its edges, and a regular graph is a hypergraph of degree 1. So this is an example of a regular graph, like, for example, the ones that we used for part-of-speech tagging, where essentially between each node we had a single edge corresponding to a transition between 2 part-of-speech tags. So one way we can formulate the problem of parsing is to form it as a version of hypergraph search. So if we think about the ambiguous phrase, I saw a girl with a telescope, we have a couple ways we could parse this. One way we could parse this is say, I saw a girl with a telescope. So this is basically saying I saw, and it's using a telescope. And another way you could parse this sentence is I saw a girl with a telescope. So this is a noun phrase saying there's a girl holding a telescope, and then that is what you saw. So there are 2 choices at this phrase here about the children that could appear in this tree. One child child edge could be this red edge giving us one parse. Another child edge would be a blue edge giving us this parse. And so what we want to do is we basically want to search through a whole bunch of candidates for these graphs encoded as a hypergraph. And the highest scoring candidate would be the parse that we eventually get in the end. And if we calculated the partition function using all of the graphs, that would basically allow us to do training using a CRF style algorithm. So weighted hypergraphs allow us to do this. And basically, like graphs, you can add weights to the hypergraph edges. For example, being a negative log probability of choosing that edge. So we might have the negative log probability of the verb phrase generating a verb and a noun phrase and a prepositional phrase, and also the negative log probability of a verb phrase with just the verb and the noun. And this can be formulated using the So basically, the search over these graphs can be solved using dynamic programming algorithms. So one stereotypical example of such a dynamic programming algorithm is something called the Cky algorithm, which finds the highest scoring tree given a context-free grammar. And the way it works is it creates a hypergraph containing all of the candidates for a grammar and does search over them. So if you remember from the CRF class that we talked about before, essentially we would create scores, and the scores would be the sum of the previous best scores, and the score for the particular edge transition that we are handling. The only difference between this and a hypergraph is now instead of having a single best score like we had for search, using the Viterbi algorithm or the forward-backward algorithm, now we have multiple best scores where each best score corresponds to the score of one of the children here. So this is analogous to the Viterbi algorithm that we talked about before, but we're doing search over hypergraphs instead of individual graphs. And similarly, like I just mentioned, we can use this to calculate the partition function. And so the way we do this is we have a marginal probability of each span given a CFG grammar. And the partition function allows us to calculate the probability, or is the probability of the top span. And so this is the same as the CKY algorithm, except instead of using max, we use log sum exp. So this is exactly like the difference between the Viterbi algorithm and the forward-backward algorithm that we talked about for CRFs. So once we realize this, we can then apply the CRF-based algorithms that we had for sequence labeling directly to parsing. And there's a method called neural CRF parsing, which was kind of one of the early applications of neural models to constituency parsing. One early application. There were other methods as well, but yes. So the way it worked is basically it predicted the score of each span using a feed-forward neural network, and then it did structured inference using the CKY and the inside-outside algorithm. So the way it works is we basically take a model here, we do feature extraction with it, and then for each of the spans, we get a score that's calculated based on the span and the children span, the child spans, etc. And then after you've done this feature extraction, you do CKY in discrete space. So this is an application of the CRFs that you already learned for sequence labeling to kind of tree-structured inference. But there are actually now even simpler methods that you could use here. And the basic idea is to get rid of the structured training algorithm, get rid of the CRF, and simply try to decide whether a span is a constituent in the tree or not. So the way it works is essentially you have positive examples that correspond to spans that are in the tree. So like you might have a sentence, a noun phrase, a verb phrase, and other things like this. These null spans are basically kind of like spans that correspond to multiple syntactic constituents. And then you have a bunch of other things that are not spans whatsoever. So for example, this part of the verb phrase would not be a span. So that would be like a negative example that you would want to demonstrate here. And once we create this formulation, we can just essentially predict these spans or not. And you can also do other inference algorithms like the CKY algorithm, dynamic programming, or even just a simple top-down algorithm that chooses which span you want to pick first and then splits going down the tree. So it allows you to even simplify the problem. So kind of the one of the state-of-the-art methods in this space right now basically does a very similar thing, except it's using now self-attentional models or BERT or other things like this. So if you want to create a structured, if you want a constituency parser, this is kind of one good way to do it. And this is implemented in the Berkeley self-attentional parser. Okay, in the final part of the talk here, I'm going to be talking about neural models for graph-based parsing, specifically dependency parsing. And to give an idea of what I mean by this, essentially the way these models or methods work is we express each sentence as a fully connected directed graph and score each edge independently like this. And then we run some sort of dynamic programming or other variety of algorithm to find the maximal spanning tree. So this, in a way, is kind of the equivalent of the methods that I talked about for phrase structure parsing, except applied to dependency parsing. And one algorithm that's widely used for finding the highest scoring spanning tree is the Chu-Liu-Edmonds algorithm. And this algorithm, I'm not going to go into all of the details here, but just give a general idea. And so we have a graph and we want to find its spanning tree. And basically what we do is we greedily select the best incoming edge to each node and subtract its score from all incoming edges. If there are any cycles, we select the cycle and contract it into a single node. And then we recursively call the algorithm on the graph with the contracted node. And then finally expand the contracted node, deleting an edge appropriately. So you don't really need to know the details, but basically what this can show you is there are algorithms that take in this scored graph and turn it into a tree that could then be used as a dependency tree. So then the main question becomes, how do we score this tree in the first place, or score the edges in the tree in the first place? So there's lots of different ways to do this, but basically the general idea is that we want to extract features from the sentence for each word, and then we want to compare the features between each word using an MLP to try to figure out, essentially which edges exist, which edges do not exist. And one way we could do this is with a bidirectional Lstm model. And another method, we could do that with a bidirectional Lstm model. So then the question becomes, once we've extracted the features, how do we get scores from them? And one particularly widely used and effective model for doing this is the Ethane Classifier. So the way it works is essentially we calculate the hidden state for all of the words when they are being used as dependents, and then we calculate the hidden state of all of the words when they're being used as heads. So basically the type of information to determine whether something is a good head is probably different than the type of information that should be used for a good dependent. And then we run this through a scoring function and get the score for an arc. And the way the arc score works is we have the head and the dependent, and we calculate a bilinear correspondence between them. So we have the dependent vector along with the head vector, and we have a matrix in between to calculate the score. So this is a little bit like attention, essentially, like the bilinear attention that we talked about in the attention class. And then we also have just basically a vector that is multiplied in with the heads. And the vector, what this says is whether the head is likely to be a head in the first place, or whether the word is likely to be a head in the first place. So once we have this functional form, we basically optimize the likelihood of getting the correct parent. So we calculate the score of arcs for each child or each dependent here. And we try to maximize the negative log likelihood of picking the correct head. And so this is a local model for prediction. and it has a global decoding using a maximum spanning tree algorithm at the end. And this gave very good results on a universal dependencies parsing task and is still widely used since its introduction in 2017. Here's an implementation if you'd like to take a look. So one final thing is that these graph-based models can be globally trained as well. So basically, we talked about global training of like phrase structure parsers. And one way that we can do this is using something called global probabilistic models. And the way they work is like we talked about before with CRFs. We calculate the score of each, structured output, parse tree, for example, and we try to maximize its probability. This can be difficult, as we mentioned before, in the general case, but for first-order graph-based parsing, if we have, we can use different ways of basically calculating this partition function, and I won't go into the details. But there can be bottom-up CKY style algorithms, and then there's also something called the matrix tree theorem that allows you to compute marginal probabilities over directed graphs. So basically, long story short, if we want to optimize the models in order to maximize the probability of getting the correct spanning tree, we can actually do that using some tricky math or dynamic programming. And these were applied to neural models in Ma et al. 2017. Okay, so I talked about incremental parsing, and I also talked about two varieties of dynamic programming or kind of algorithm-based methods for doing global training or global decoding over models like kind of like CRF-style models. At the same time, there's an alternative of parse re-ranking, and the basic idea is if we have a nice model for kind of like global scoring of trees, but it's hard to implement a dynamic programming decoding algorithm, one thing that we can do is we can try re-ranking. So what we do is we generate with an easy to decode model like a incremental parsing model or something like this, and then we rescore with our proposed model that doesn't have a clear dynamic programming algorithm or incremental reduction. So there's a bunch of examples of re-ranking. There's something called inside-outside recursive neural networks that calculate representations using an algorithm that looks like the inside-outside algorithm that's used in re-ranking. There's also parsing as language modeling, where they essentially create a language model over parse trees and use this to re-rank another parser. And there's something called recurrent neural network grammars, which are basically language models that incorporate parse structure. And all of these can be applied. However, there's one word of caution about re-ranking, which is that you might come up with a very nice model that has some sort of theoretical advantages or something like this, and it gets state-of-the-art results on parsing. But it might also be kind of an implicit effect of model combination between whatever model you use to generate the original outputs and the final downstream model that you proposed. And so the model generating the parses basically prunes down the search space, and then the ranking model chooses the best parse only in that space. And there's a nice example of this in Fried et al., where they combine a discriminative parser with a generative parser, where they generate candidates from each of the models and then re-rank. And you can see that essentially when you generate with a discriminative model, which is easy to decode, and then re-rank with a generative model, you get very nice results. However, if you generate with the generative model and then re-rank with the discriminative model, it does better. But overall, if you generate with the discriminative model and score with it, and generate with the generative model and score with it, you can see that the discriminative model does better. So basically, long story short, there could be an implicit model ensembling effect here that you need to control for whenever you're doing re-ranking. And this is also true for re-ranking for other types of tasks as well. So like, let's say you come up with a machine translation model that uses a regular machine translation model to generate some outputs, and then you rank it with some other fancier model. It might be the case that just this combination of the models is getting you most of the gains. So that is all I have for today. And in the discussion, I'm thinking maybe I'll go a little bit deeper into some of the syntax-based resources and show you, the Universal Dependencies Tree Bank and other resources that we might use there. And then we can, ask questions or look at the syntactic structure and stuff. So instead of a discussion, it'll be more like a walkthrough data and better understanding of what syntax looks like, etc. So thank you. That's all we have for today.